Welcome to an in-depth look at SQL, the language of civilization. We'll explore a comprehensive history of structured query language and its evolution in data management. The history of the structured query language, SQL, is not merely a chronicle of syntax evolution or a catalog of software versioning. It is the definitive narrative of the information age. From the hierarchical checklists that launched the Saturn V rocket to the vector embeddings powering modern generative AI, the trajectory of data management reflects humanity's increasing ambition to organize, query, and manipulate the world's information. This report provides an exhaustive, expert-level analysis of this evolution, tracing the technical, commercial, and theoretical developments that establish SQL as the intergalactic dataspeak of computing. We examine the early dominance of IBM's Information Management System, IMS, and the navigational paradigm, the theoretical rupture caused by Edgar F. Codd's relational model, the fierce database wars of the 1980s and 90s, the NoSQL rebellion, and the modern renaissance of SQL in distributed and AI-centric architectures. By synthesizing historical records, technical benchmarks, and market dynamics, we reveal how a language designed in the 1970s managed to survive every technological paradigm shift, to remain the bedrock of modern digital infrastructure.
The pre-relational epoch and the Apollo catalyst, the tyranny of the tape and the navigational imperative. To understand the liberation SQL provided, one must first understand the prison of early computing. In the 1950s and early 60s, data processing was literal. Data lived on magnetic tapes, which were sequential access devices. The physical medium dictated the logical operation. If a business wanted to update a customer's address, the computer had to read the entire customer master tape, record by record, until it found the matching identifier, write the updated record to a new tape, and then copy the rest of the old tape over. This was the master file update cycle, a slow, batch-oriented and brittle process that coupled the application logic tightly to the physical storage medium. The breaking point for sequential processing was the space race. The Saturn V rocket, the machine destined to carry humans to the moon, was a beast of complexity that exceeded the capacity of manual filing systems and rudimentary flat files. It contained over 2 million distinct parts, each with version histories, suppliers, and engineering specifications. The logistical nightmare was profound. If a specific valve in the second stage was redesigned, engineers needed to instantly identify every subassembly that utilized that valve. In a sequential tape system, answering this query required scanning millions of records, a latency unacceptable for the pace of the Apollo program.
In the early 1960s, the race to the moon was on. NASA needed more than rockets and astronauts. It needed a way to manage the staggering complexity of the Apollo program. In 1963, IBM stepped in. At the North American Rockwell plants in Downey, California, two engineers, IBM's Yuri Berman and Rockwell's Pete Nordyke, began building something revolutionary. What started as a tool to track parts for the Apollo command and service modules soon evolved into a system that would change computing forever. By 1968, their creation was officially released as the Information Management System, or IMS. This wasn't just software, it was the backbone of the lunar landing, and it became one of the very first commercially successful database management systems. IMS mirrored the real world in its design. Imagine a rocket. It has stages, each stage has engines, and each engine has valves. That's exactly how IMS stored data, in a hierarchy. To retrieve information, programmers had to walk through this tree using commands like GU, get unique, or GN, get next. But there was a catch. If the database administrator changed the hierarchy, every program built on the old path could collapse. This challenge became known as data dependence, a bottleneck that haunted developers for years. Yet, despite its rigidity, IMS was lightning fast. Instead of searching, it jumped straight to memory addresses on disk. That raw speed made it indispensable. And here's the twist. IMS didn't fade into history. Even today, in 2025, it quietly powers billions of transactions in banks and insurance companies around the world. From the moon landings to modern finance, IMS is a reminder that sometimes the tools built for one great mission can end up shaping the future in ways no one imagined.
Alongside IBM's hierarchical IMS, the CODASYL group, known for COBOL, introduced the network model. Unlike IMS's strict tree structure, the network model allowed records to have multiple parents, forming a flexible graph-like design. However, this flexibility came at the cost of complexity. Programmers had to navigate databases through intricate pointer chases, making database management a specialized, almost arcane skill. The industry soon recognized the need for a breakthrough, a way to separate logical data from its physical storage.
The revolution arrived in 1970, not from a product announcement, but from a research paper titled A Relational Model of Data for Large Shared Databanks, published in the Communications of the ACM. Its author, Edgar Ted Codd, was an Oxford-educated mathematician working at IBM's San Jose Research Laboratory. Codd observed that the existing hierarchical and network models were forcing programmers to constantly repair their applications whenever the database schema changed. He proposed a radical shift. Data should be represented not as a hierarchy of pointers, but as mathematical relations, tables containing rows and columns.
The history of SQL isn't just about syntax, it's the definitive narrative of the information age itself. We'll begin by examining the early days and the pivotal shifts that occurred. IBM's Information Management System, or IMS, once held early dominance with its navigational paradigm. 80s and 90s saw fierce competition as different database systems vied for supremacy. The NoSQL rebellion challenged traditional database approaches, introducing new paradigms for data storage and retrieval. Today, we see a modern renaissance of SQL in new and evolving architectures. SQL is thriving in distributed architectures, essential for scalability and resilience in large-scale systems. It's also powering AI-centric architectures, handling everything from vector embeddings to complex data manipulation for intelligent insights. In conclusion, SQL's journey is a testament to its enduring power and adaptability. Despite countless technological paradigm shifts, SQL has not only survived but flourished. It remains the indispensable bedrock of our modern digital infrastructure.